So last time we looked at diffusion of carbon in FCC ion. Again, the reason we're looking at this is because for metallurgy, mostly we're still looking at steel. Of course, we look beyond steel now, aluminum, magnesium, alloy. But steel is a big part of material science. So if you look at the phase diagram between iron and carbon, you can see for the ferrite, alpha or the BCC, one has a little bit of solubility, carbon has a little bit of solubility in BCC iron, but has a huge amount of solubility in austenite or gamma phase or FCC iron of up to 2.14 weight percent. So you can imagine carbon is going to be more comfortable in the FCC structure. We look at both BCC, FCC. We look at their interstitial sites. For each one of them, there's a tetrahedral site, there's a octahedral site. We spend most of the time on FCC. We look at why carbon is more comfortable in the octahedral site because the bond distance is closer to the equilibrium one, but much shorter in the tetrahedral site. We also looked at when it jumps from one octahedral to other octahedral, which path it's going to take, because that's very relevant to this course. It's about diffusion. Like carbon is going to diffuse from one octahedral site to empty interstitial site. So we did that last time. But as we mentioned previously, the diffusion, we generally have vacancy diffusion shown over here. We have interstitial diffusion, which is shown over here, and we have interstitial C diffusion. So specifically look at it, we use the carbon diffusion iron as an example to look at this interstitial diffusion mechanism. For the vacancy diffusion mechanism, okay, it's actually pretty straightforward. There's a vacant site that over there is just going to jump, and the jump distance generally is shorter compared with interstitial jump, as you can imagine. From one interstitial to another interstitial, sometimes it's longer. Okay, so but something we didn't talk about is how hard is it to create a vacancy? Because we sort of touched upon how hard is it to create interstitial site. Last time I think I gave you two numbers. If you put the carbon in the octahedral site versus the tetrahedral site, the energy is lower by 1.5 eV, so that's a lot. But what about how much that energy does it take to create a vacant site, like shown here? Let's say we have iron here. Why it prefers a vacancy? Hand waving, we're saying, okay, because entropy, right? So you create a vacant site, your configuration entropy is now zero now because you have two species and one species. So you have the gain in the configuration. So we're going to be looking at that. But overall idea is how much energy does it take to create a vacancy? Because the other penalty would be when you remove iron from the structure, you're actually going to cut. If it's BCC, you're going to cut. Let's say we have 6 physics. It's going to cut 6 iron bonds. So actually, there's energy penalty for you to remove iron atom from BCC iron. But at the same time, you're gaining the entropy. The entropy now is non-zero. So we want to quantify that. But before we do that, let me show you a table. What does the result look like? Okay. So this is a table from one of the reference books that I put in the syllabus. So this is how much energy does it require to create a single vacancy, like 1B, a single vacancy. So these are the experimental techniques which were used to measure this, most likely, and nowadays mostly it's done with PS, a positron absorption spectroscopy, because basically you generate a nuclear reaction to create positron, and when it goes into the structure of ICC's defect, it gets absorbed, and then we know how many do we have and how fast they get absorbed. So we're not going to be focused on that, but let's look at this concentration of not concentration. This is the fraction of vacancy in the material. So the way we look at that is this is at melting temperature. So let's say for iron, iron is not here. Let's say aluminum. At melting temperature aluminum, the vacancy is about 10 to minus 3, so 0.1%. At very high temperature, that's actually quite significant. A lot of vacant iron were created. And for most of this material, you can see at melting temperatures are about 10 to minus 4, 10 to minus 3 range. But what about these two numbers, entropy and entropy? Because earlier I said we want to look at how much energy is going to require to do that. But we get two different numbers, entropy and entropy. So we want look at what's the meaning between these two parameters. Okay, so let's look at again review our regular solution model, because we can easily use our regular solution model to understand the physical meaning of these two parameters. Again, that's why we do thermal first, and then we do diffusion. So for the regular solution model, from last semester, we know the free energy of mixing can be written as the entropy of mixing minus TES, the entropy of mixing. For the entropy of mixing, what we had was basically omega XA 1 minus XA. And entropy of mixing, if you check your notes from last semester, is basically minus R XA of XA plus 1 minus XA of 1 minus XA. So last semester we might be using minus AB, but that's just one we're counting the numbers, the other one counting per mole. So it's just what the reference for the amount we're using. It's basically the same. So why is this relevant to what we're looking at here? So in the regular solution model, think about a regular solution model. We have two species. We have A and then we have B. That's why we have XA over here. A, B, A. So I think I kind of talked about this last time. If we treat A as one species and B as another species, if it's like a binary analog, I think it's very obvious. But this can also be applied to the vacancy, because A can be a vacancy, B can be the species we're dealing with. So here we're looking at the vacancy like in aluminum. Right? So basically, XA is going to be the vacancy. So we can borrow what we have over there and look at how much energy is going to require to create a vacancy. Okay? So what we can write is, by mimicking what we did for regular solution model, we can write delta G is delta H minus T delta S. Let's say we're dealing with vacancy, so instead of going with mixing, we're basically doing the vacancy capital V over here. So for the delta H, V, basically we have the same term, omega XA 1 minus XA. But now A is vacancy, so XA is basically XB. And if we have just a little bit of vacancy, you saw the number, right? Even at melting temperature, it's 10 to minus 3, 10 to minus 4, so it's a very small number compared with 1. So basically what we can do is we can say this is essentially can be approximated by XV, because what omega XV? Because what we have XV, omega XV, 1 minus XV. But XV, this is a very small number, right? 10 to minus 3, 10 to minus 4. So 1 minus XV, we can approximate that as 1. Then we're left with omega XV. So that's for the entropy part. For the entropy part, we have the same entropy of mixing, because by creating 2 species instead of 1, we have this entropy of mixing, also called configuration entropy. So we can simply copy that term down here, but replace XA by XV. At the same time, what we have additional term that is not there in the regular solution model is about the vibrational entropy. So basically, in last semester we talked about dealing with solid. The solids characteristic for solids is vibration, because they're an order structure, so atoms are vibrating. When they're vibrating, we have vibrational entropy, we have vibrational energy. The regular solution model, we didn't include them. But in the real case, we should include the vibration entropy. So when we have a perfect, pristine iron, we have, for all the iron atoms, they're going to have certain vibrational frequency. But once you remove one, or not one, you remove some of the iron, you create oxygen vacancy, the iron, the vibrational frequency is going to change, right? So which means the vibrational frequency, vibrational entropy is going to change. So without going to the details, we can say, okay, so approximately we can say we have entropy change. So this is lowercase v, so this is vibration. So don't want to confuse with this v is vacancy. They look almost the same, but one is capitals, the other one is a mu. I call it v, but it's actually mu. But we're on the same vibrations, so I'm just going to call it mu. So this is the vibrational entropy difference between a pristine and a defect material. And if you have this many vacancies, then we have the total vibrational entropy change. We can approximate it as simply has a linear dependence. Again, when XB is small, we can do this. Of course, you'll be wondering, okay, where does that come from? So it can be computed, but experimentally, we have we're going to see this term later. We're going to see where it's going to show up. But it's something that accounts for the difference in terms of vibration between a pristine crystal versus a crystal that has some vacant sites. So as we can imagine, the vibration will be different. That's why we have that term. Okay, so we have 2 terms: the entropy term and the entropy term. So if we plot this as function of xv, what we can see is for the delta H, it's very straightforward because it's basically xv multiplied by omega, so it has a linear line going through the origin. But for the entropy term, we looked at this one last semester, we know it has its parabola shape. But we have actually, so this is a parabola with a shift. But overall, for the minus t dot SV term is going to look like this. So that term is a parabola on the top because we have, that term is, this is less than 0. So let me think. Yes, this is less than 0, so entropy is positive. Delta SV is positive, so we multiply that by minus t, so that's why it becomes negative. And so of these two terms, one is going to go up, one is going to go down. So if we look at the summation of these two, basically we're looking at something like this for the delta G capital V, which means it has a minimum. So the free energy change has a minimum at a certain composition for the vacancy. So we call this XV equilibrium or asterisk or star. So this is going to be the equilibrium composition. Again, why does this exist? So the reason is when you create a vacancy, there's a penalty, energy penalty, because you cut in the bounds. So the system does not want to do that. At the same time, because when you create a vacancy, you increase configuration of entropy. So there is an advantage, this benefit of creating vacancy. So you can see the trade-off between the two competing factors, which means there exists XV somewhere in the middle, which is going to balance these two opposing forces. And that's the equilibrium composition. So that's the this C equilibrium. That's where it's coming from. So how do we get that XV equilibrium? Mathematically, we already know that is when the this delta GV is at the minimum, and we know how to deal with minimum, right? So this is a global minimum, extreme point. So which means the slope is 0. Slope of the tangent is 0, which means mathematically it becomes pretty straightforward. Let's just take the derivative of this and make it equal to 0. And we have delta GV, right? So by taking the derivative, that's not hard for the delta H. V, basically, we're taking the derivative of XV, so you basically get omega. So actually, let's write it down. What does this look like? So we have omega. And we're taking the derivative of minus, okay, so minus Ts. So we have minus T, so we have RT XV log XV plus 1 minus XV log 1 minus XV minus T XV delta SV. So basically we're for the minus TDS, we're taking the derivative over this, and we have a log term. We know how to take the derivative of a log term, which is d log f dx is 1 over f df dx. So this is multiple times last semester. And then we're also gonna use the product rule because the xv multiplied log xv, both of them depend on xv. So we use product rule as d f g dx as f dgx, egdx plus g df dx. So we can do the derivative. So we're gonna skip that, and this is what it's gonna look like in n minus t ds v as rt log x equilibrium. So if you take the derivative of those two terms, this is what you can get in the end. For the derivative of dg delta g dx. So from this, what we can get is basically log x v equilibrium as delta S v of r minus omega over rt. Right, and then if you want to get the xv equilibrium, we take the exponential on both sides. Then we get xv equivalent to be exponential delta SV r exponential minus omega rt. So this omega, we can replace it as delta HS, delta HV. So recognize it's going to be the entropy term, it's energy term. And then with this, and let's go back to that table. I think the table is using different notation. The table is using H, F, and SF. So basically, the delta SV is SF in the table, and delta HV is HF in the table. So F here, I think it stands for formation. Didn't say it this way, but this is formation entropy, and this is formation entropy. But they correspond to the delta SV and delta HV we have over there. So with these two terms, what you can see is if we have these two terms, we can simply ask, okay, if you already have these two terms, you simply ask at room temperature, what is going to be the fraction of vacancy, and then we can get a number. And at melting temperature of a specific material, what is vacancy composition? So basically that's where the silicon is coming from. So the material properties are going to be this column and that column. With these two, you can get the vacancy composition at any temperature. This column is only listed at the melting temperature, but you get the idea. We can get it at any temperature. So the reverse problem would be, okay, so let's say experimentally we measured XV equilibrium at different temperature. So you have a material and you take it to national lab, because some universities like the Bowling Green, they have a positron absorption spectroscopy facility. You take it over there, and you measure the composition of vacancy at different temperature or daytime measurement, and you know it's going to satisfy this equation. So now I want to ask you, if that's the case, how do we get delta SV and how do we get omega? So you went there, you drove there, you flew there, and did the measurement. You have the vacancy composition at different temperatures. Let's say from room temperature to 900 Celsius. And then you measure all of those, and you know the temperature dependence of the composition is going to satisfy this equation. So the question is, how can you get delta S and omega so you can put in the table in those two columns? So this is not a question to diffusion. It's a generic data analysis question. So you already have the data at different temperature. We have a column. Okay, so we have 300 Kelvin, 10⁻⁷, 400 Kelvin, 10⁻⁶, something like that. Keep going. And we know it has this dependence in terms of temperatures. How do we get delta SV and how do we get omega or delta HV? Anybody? You all have done some experiments, got some data, and the purpose of getting data is not to get those data, it's generally we want to analyze the data based on something that's useful, and then becomes more generally applicable to other scenarios, right? So here is how do we extract delta SV and omega if we already know how that SV depend on T. Anyone? Okay.
Is delta SV and omega is unknown?
Unknown.
Yeah, so if we got two pairs of the data,
Not too
like
bad, like maybe 7 pairs.
yeah, so if there's more pairs of the data, then we can go and to like given the xv as the ln xv, so that we can do a linear equation, and then we can fit.
Okay, we have log
Yeah.
here.
Yeah,
Fit,
yes.
how you gonna fit it?
To fit a ln xv with 1/t,
1/t.
because this is a linear equation, and then we can get the number of delta SV and omega.
So you're saying this is a linear equation as A plus A minus B over T.
Yes.
So we plot natural log XV as function of 1/t.
Yes.
And because the equation is saying log xv to 1/t, this is linear equation, so A plus minus B. So or make A minus BX, so it's gonna look like this. Right?
Yes.
And so from the intercept, you get A, right? From the slope, you get B. So A is delta S, B over R is a constant. 0.34. And B is omega over R, which is, and then R into constant, you can get omega. So that's how you, that's how this table was presented, basically. They did all of those, and then they extract these two numbers, put it in here, and once you have this, what is use of this? You can get composition at any temperature. So over here, just list that one temperature, so you get an idea what's orders magnitude for the composition, even at the melting temperature. So not a lot of them, but there's still some. Another thing would be, okay, so about the magnitude. So this is gonna be the entropy of forming a vacancy. We're just see some numbers, but we have to make sense of them, okay? So do we consider this number to be large or small? 0.7 eV. Is that? So if you want to categorize, okay, so because it has the entropy of forming a vacancy in aluminum is 0.7 eV, should we consider vacancies easy to form or hard to form or mediocre? So that's the question. So we'll see some numbers, right? Again, we're just not gonna be limited by this number. We want to use it. We want to think about, okay, that tells us the material is easy to form the vacancy. Okay, so we have to be careful because it tells us it's easy to form, then we might have a lot of vacant size in there that might affect our property because that implies aluminum is going to be able to diffuse. Once you create vacancies, they can be diffused. And is that a good thing or bad thing? Really depends on application. But we should have some general idea about, is it high or low in terms of the value? What's your take on that? 0.7 eV, is that high or low or medium?
Medium.
Medium. The reason?
Just us.
Just us.
I don't know.
Just guessing. Okay, so we need some reference. Right? We need to put this into some context. For example, first saying, okay, for let's say for a newborn, okay, so let's say he or she can understand, but we're gonna say, oh, we're gonna take a ride. We're gonna drive at 100 miles per hour, right? So for that newborn has no idea whether it's fast or slow, right? Just he or she does not have the context. It's never been in the car. But if you be in a car for a couple times, you look at the meter up there, and you have an idea of, okay, so maybe 100 is really far, because I can see the speed limit is okay, 70 miles per hour. 100 miles is really far away, or in the car is going really fast. It gets nervous, because that's fast. So that's the context I'm talking about. So we're also gonna need some context of thinking about, is that 0.7 EV a large, small, or medium number? Okay, so different people have different ways to put this into context. But one way to think about it is to think about in terms of a thermal energy. Okay, so what I mean by that is 300 Kelvin. Okay, so 300 Kelvin. How much energy is 300 Kelvin? Why am I saying energy? Why I'm talking about temperature? Because kVT is what we call the thermal energy, right? Thermal agitation. Because we're in the environment with constant temperature, so we're constantly being injected with this amount of thermal energy. So for that's why we are saying 300 kV means energy, because we can simply multiply by kV, you get energy terms, kVT is energy term. So 300 Kelvin is 0.025 EV or 25 EV. which is a good reference we want to keep in mind as the material scientists. We know, okay, so 300 Kelvin is basically 25 millieV. So 12,000 Kelvin is going to be 0.1 eV. So 0.7 eV would be 12,000 multiplied by 7. So that's actually quite significant, which some people would call it high, yeah, but most people would just call it medium. So you guys think it's correct. 0.7, people generally call it medium. So something that can happen if you provide the thermal energy. On the other hand, for the 4 eV and here for tungsten, people consider this is a very high formation energy. Very difficult to form vacancy in tungsten. Not just because it has high melting temperature, simply because the bond is just so strong. So the energy penalty is just so much. So that's that table, okay? And then after looking at the metals, look at different metals, look at vacancy, look at interstitial, and let's look at something beyond metals. Like here for the ionic crystals. Okay, so we have a bunch of ionic crystals here. Most of them are these are like halides, metal halides. And you can see here we have again something about H, something about S, and we have different types of disorder. So we want to explain what are the Schottky and also the Frankel defects or disorders. Is anyone of you familiar with Schottky and Frankel disorder? So what does Schottky disorder mean?
Is that the one that has both the anion and cation vacancy?
So the way to think about that is, think about the SUV. Okay, so SUV, just replace that U by V, so it's SVV. So Schottky is going to involve two vacancies, two V's. So you have to replace SUV by SVV. So what does that mean? Let's look at the schematic here. So we have anions shaded and cations. So think about like a sodium chloride. We can have a perfect crystal, but again, perfect crystals, there's an entropy penalty. So what we can do is we can remove the cation, like here. So there should be a cation or positive ion here, but we removed it. So by removing that, we have to break, on the 2D, we have to break 4 bonds, ionic bonds between the positive and negative. But if we just do that, we have a problem, because when you take one positive ion out, it's not bad, it's charge balance anymore. So the system's not going to be happy if you just simply remove one positive ion. So we need to also remove negative charge, which we can remove anion or negative ion from here. So we can keep it neutral. So that's why these all appear in pairs, because the defects are charged. Previously, the carbon in iron is not charged. The iron, move vacancy from iron, that's also not charged, because basically it's shielded by this electron cloud. So each ion is actually we can think of that as neutral. But for the ionic crystal, we cannot simply remove one cation or one ion. We have to remove them in pairs. So if we remove a vacant cation, will create cation vacancy, at the same time create anion vacancy. So this is what's called Schottky defects or Schottky disorder. So SVV with 2 vacancies. Another alternative would be we don't remove the cannon, we simply displace it. For example, we should have a cannon over here, but we simply displace it into interstitial site. And it's supposed to be here, but because it can move, so it actually moves over here. But that's interstitial. So once you do that, you create an interstitial, but you also create a vacancy. So again, it's a pair. You've got two defects. One here, one there. You can see that's totally different from the rest of it. So this is what's called a Frankel disorder, Frankel defects. So Schottky SVV. So we have two vacancies. The Frankel, we have one interstitial and one vacancy. So if you come back here, then what you can see is, okay, so it basically tells us for all these alkaline metals like lithium, sodium, potassium, primarily it's Schottky defects. But for silver-based halides, it's Frankel. And you would think, okay, so why would that happen? Because silver is supposed to be much bigger than the lithium or sodium. So why it wants to form the interstitial instead of a vacant site? Because actually it's counterintuitive because silver actually is quite small in the outer crystal. So that's why it wants to form the Frankel defects. And also there's still these two columns, SP, now you can see SP, S stands for the Schottky, and F stands for the Frankel, and we also have an enthalpy term and entropy term. So where does that come from? Okay, so I'll explain about that. But before I do that, there's another thing I forgot to mention was it's about this. About the vacant site. So that's one method to get that expression. Another method would be we use, so I'm gonna circle this because we're gonna come back to this later. The other method would be to use what's called the laws of mass action. So this is what does it mean. So I'm gonna write down a chemical equation. Okay. Laws of mass reaction, so this is going to be a vacancy creation reaction. So now here is, okay, so we create a vacancy coming from that spot. So that spot is treated as now. And we're going to create a vacancy and remove an atom, like an iron atom from here. So for this reaction, we can write down equilibrium constant. So we're going to treat this vacancy creation process as a reaction. So the V here is going to be vacancy at A is going to be the rest of the matrix. The rest of it that still has A over it, so this is not the leading one. It's just the rest of it. And they're sitting in the equilibrium position. Again, why we're saying that? Because we're saying if you remove certain amount of A create a certain amount of vacancy, it reaches the equilibrium state because the energy penalty and energy gain, they're balanced, which means the vacancy and the rest of the A atom are forming a chemical equilibrium. So we're gonna write down that chemical equilibrium, and then for a chemical reaction, if it's in equilibrium, we can write down equilibrium constant, which is basically from the loss of action would be XV. That's gonna be the concentration of the vacancy multiplied the concentration of A, which is 1 minus XV, because you already moved XV part, so the rest of A is gonna be 1 minus XV. So we can write that down, and again, because XV is small, we can approximate this as XV, which basically tells us XV is approximately 2K. And from the loss of mass action, we know delta G, we can write it as minus RT log K. Here, but remember that's correct. So which basically is saying K is exponential minus delta G over RT. So delta G we can separate into the delta H minus T delta S. So what we have is exponential delta S R exponential minus delta H RT. Again, we know that's basically XV. So you can see we get exactly the same result as what we had previously. So let's circle this. You can see these two results are identical. One, we look at the way to balancing two energy terms. The other one, we simply treat that as the equilibrium reaction. Write down the equilibrium constant, and we know how to go from delta G to equilibrium constant from our physical chemistry class, and then we can get exactly the same equation for the concentration. So we're going to use the same idea for the Schottky defects. So let's say sodium chloride. So we can write as now it's going to form sodium vacancy plus chlorine vacancy. So we have the Schottky pair. So I have to explain what does this mean. This is what's called Kroger-Vink notation. So it's gonna look like, okay, we have A, we have B, we have C. So with the symbol and the superscript and the subscript, so 3 components for each defect. So the A definitely stands for what kind of defects we have. It's vacancy with capital V. And so A is going to be the type of defect. Because there's nothing there, so that's why we're writing a vacancy. C would be the charge. And B would be the site. So when we're saying the site, if you think about V and A, so that means on the sodium side, we create a vacancy, right? So that's very easy to read. On the chlorine side, we create a vacancy. So the tricky part, for most people, the tricky part is that charge, because it's counterintuitive. So when they create this notation, what they are saying is, okay, so because sodium is positively charged, so when you remove it, on on that side, before it was 1 plus, but now it's 0, because the ion is not there anymore. So 0 minus plus 1 is minus 1. So they're gonna say, okay, so that vacancy actually takes a negative charge. I think it makes sense, because when before, over there, it was supposed to be a plus 1, but now you with vacancy, so it becomes minus 1. So minus 1 is using a prime. So it's 2 charge double prime. And plus charge is using a dot. So plus 1 is 1 dot, plus 2 is 2 dots. Okay, so it's time, so I'll let you go. But on Friday, what we're going to do is we're going to finish this. After we introduce this notation, we're going to do the same thing. Write down equilibrium constant for this reaction, and then we can see where does the delta S and delta H is going to come from, and how we're going to fit into that table. Okay, that's it. Thank you.